Hi, today I want to model an inverted pendulum, and I'm going to do it in three parts. The first part, I'm modeling the pendulum, I'm modeling the parts, and then we'll move to the motion application to set up a motion simulation. And at the end, I will control the pendulum or inverted pendulum with MATLAB. So let's just start with making the master assembly. Be careful with namings. The part namings are going to be variables in MATLAB. So MATLAB doesn't accept some characters for variables, so be careful with that. Now if I move to part navigator, I see the pendulum as the master assembly and it is selected as the work part because the font is bold. Now I can move to assembly and start adding new components. The first component I want to have here is the wheel. So I double click on the part that I just made under pendulum and go to home and I start sketching. The sketch plane and the dimensions are not important for now. This is just an example. But later you can come back and change the parameters as you wish. So the wheel sketch is ready and I can extrude it. Here I click on finish sketch and click on extrude. And I want it to be wide enough so it won't fall sideways, but you can use two or more wheels instead of doing this. So the wheel part is ready. I can now go back to the master assembly, and if I now save, it will ask me for the second name because I didn't name it at the beginning. So I save the wheel part, and the master assembly is now selected as the work part, and now I can add new components. If you don't go back and select the master assembly, the new component will go under the wheel, for example, which you don't want. The next part is going to be the main body of the inverted pendulum. Double click on the new part, go to home, and start sketching. I start sketching on the same plane because it's just easier. Here I keep some distance to the wheel and I need to add some constraint. I want this point to be on this circle and the other point is okay. Click finish and zoom out. Now I can extrude the main body. But I just want to select the regions that I need. So I go back to selection, I deselect all and make sure that the filter is set on region boundary curves and select the curves that you want to extrude. The extrude is the same size as the wheel, but doesn't need to be. You can select anything you want. And as I said, you can always go back to the sketch here and change the size of the body or other parts that you want, or add new parts or remove parts. And if I save now, the Linux is asking me for the second name, which is the body. So it's now ready and I can move on to the motion app. But before we go there, I want to change the color of the parts so it's just easier to distinguish. So I paint the wheel brown and also the body maybe with another color, so it's just easier to see. Let's go with blue. and this is how it looks like. So before I forget, we also need a ground to check the controller or verify the motion. So before I move, I have to add another part, which will be the ground. So I go to assemblies, new component, add another model, double click, and start sketching. I select the same plane, and I'm gonna have a ground maybe with a slope like this. Here I can offset this. I can offset this line with, let's say, 20 or 100 to the other side. Click OK, and then I close the caps. I'm just making this ready for extrude. So this is the profile of the ground I want to use. Click Finish and extrude. Ground should be bigger than the pendulum, so we're sure that we have enough space. Let's make it 1000. So we have enough space for the pendulum to move around. Now we need to move them to initial condition that we want to import to the motion application. Let me hide everything except the solid body so we have a better view. For example, the wheel should be on top of the ground before we move into the motion, and we should position it the way we want it to be positioned in time 0. So moving here to the wheel, first I need to add some constraint, or I can just select them and move them, but it's easier to constraint them together. Here in the assembly, you can go to assembly constraint. I'm going to use this concentric and keep these two circles concentric, and then I use touch the way that this face touches the ground face. So I can center the pendulum on the ground. So I go with the center 2 by 2. I want to put these two faces in center of these two faces, and now it's centered. So now we have the inverted pendulum model, and it is correctly placed. So I can move to the second part, which is modeling this in a motion simulation. I move to application and I click on motion. Here you need to add a new simulation and name it as you like. It will ask you if you want to component-based simulation, which means that you want to bring in your assembly from the modeling application. If you don't select this, you have to model everything again under this geometry tab. You can start joint wizard. It will automatically import the joints based on the constraints you did in the assembly. I don't have much constraint, so I don't need to check that. And here I can start making the simulation. Before we move on, I need to change this solver. The solver is now on SimCenter 3D Motion, which is actually a good motion simulator, but the connection to MATLAB Simulink is limited. So I move to Recordine, and now you see that the options available are a little bit different. So I move on to adding parts to motion bodies. Motion bodies are basically objects. Everything can be a motion body. For example, the ground is a motion body, and I want to fix it so it doesn't move around, and I name it GR as the ground. Click apply. The next motion body is the body of the robot. You can add multiple parts to the motion body. So if the body had a head part, you could select both of them and they would act as a rigid body. I name it body. I don't need to fix it. Click apply. And the last motion body we have here is the wheel. Now on the motion navigator, you see three bodies and one joint. The three bodies are the bodies, motion bodies that we have in the simulation, and we only have one joint, which is a fixed joint, fixing the ground to the space. If you open the joint, you see that all joints have two parts, action and base. If you leave the base untouched, then the action is fixed to the space. I could, for example, fix ground to something else like a wall as the base, but it's not needed here. Then the next joint that I need is my joint here. It's a revolute joint because I don't want to have axial motion. The only movement possible here is the rotational movement. And you have action and base. Basically, the action should be the part that moves more. I'm just guessing that the wheel is moving more than the body. So I select the wheel as the action. I go here and select between 2 points. I want the origin to be in the middle of these 2 points. That's why the location is on 50%. And you can see on the screen that this point in the middle is now selected. And for the vector, I'm going to use this face to represent the vector. Now you see it in orange, which shows the direction of axis of rotation. And I want the base to be this motion body. You don't need to select anything else for the base unless you click snap motion bodies. This option will, as the name implies, snaps the action to the right place the way that the origins are together. For example, if the wheel wasn't here, it was placed somewhere else, but at the beginning of simulation, you want it to be here. So you click on a snap motion body, you set the origin, match the origin of the action body, and the vector matching the vector of the motion body. And then when you start the simulation, the wheel will jump to the location you specified, and then the simulation starts. And let's name this joint motor because we want to drive this joint. We can add some friction to the joint to make it more realistic, and we can also drive it or have a motor here, but I'm going to use another option to drive this. Next, I want to define the contact between the motion bodies. So I use 3D contact, and here you can choose bodies. Remember, these are not motion bodies, so you will select a face inside a motion body. So the whole motion body won't be in contact, but only the face that you are selecting or the solids that you're selecting. And then you need to set these parameters, and you need to make sure that the contact is stable and will converge, because contact has its own algorithm and it goes inside its own loop, and if it doesn't converge, you're gonna have problem in the whole simulation. Here I want to have soft contact. To have more information about the stiffness and other parameters of the material, you can refer to this guideline for contact material in NX document. Here I'm using rubber to rubber, so it's kind of a soft contact that I'm expecting. So, and usually you don't need to change other options. I also want to have friction. I may increase the frictions both for dynamic and static to have more friction. We can also define contact between the body and the ground, even though it's not supposed to fall, but it's better for visualization. And now I can have the first run. But before you run any simulation, you have to add a solution to your simulation. There are different types that you can use. The most important ones are normal run and flexible body. Here I'm using normal one, and also I'm using controlled dynamics. If this one is grayed out for you, you need to go back because it is grayed out by default. You need to go back to the environment and then open this up and select motor drive and also code simulation if you want to run a code simulation with Simulink. Also need dynamics. If you select kinematics, you won't have any force involved in your simulation. You will only receive the motions and movements. But dynamic, you get the forces and also kinematics included in your simulation. Here I click OK, then I can go to the solution and select the control dynamics. 5 seconds seems enough. I want a more smooth simulation. This step, you can think of a step as resolution of your simulation. Then make sure the direction of gravity is correct. By default, NX is setting the direction to the Z-axis. So if you have another direction set in your model, make sure the gravity is correct. Here is downward and it is as a 1. The other parameters are usually good for any simulation, so you don't need to change anything here. Click OK and I solve the first simulation. To see the result, you can go to the result tab and click play. So here you see we have contact. The movement is as somehow it is as expected, but it seems too bouncy. So to have a quick look, you can go closer, and if you look here, the problem seems to be with the initial penetration. It happens in the first, yeah, here. Here we have too much penetration. The contact calculation is a bit complicated. I have another lecture on this, but basically the software is using this penetration depth to calculate the force, contact force, which is pushing the objects outside of each other. So here we have a lot of penetration, and the software is calculating the penetration force or contact force based on the stiffness, and that generates a lot of force which pushes this part out too much that it starts to fly. Now there are a lot of parameters involved in contact, and sometimes it gets complicated to solve the problem, but the best place to start with is this contact troubleshooting for Recordine, which you can also find on the document of the NX. So it has provided some good solutions that you can start. Here, as I said, my problem is with the initial penetration. I just need to change these maximum penetrations to manual. Basically, Recordine has 2 types of algorithms to solve contact. It's global and local. It has 2 types because sometimes global takes less time, so software won't switch the local penetration. And sometimes when the model is big or heavy, that makes a problem. So I just move it to manual and click OK. And just to set the same thing for the other contact, I can copy parameters and paste it there. And just to show you how heavy it is this part, if you double click on it, you see how heavy is your part. So I have like 300 kilograms here, and that makes a very heavy contact. So it makes sense if it bounces without setting the parameters. Now I can go back and solve again and see if that helps with the contact. So it seems more reasonable now, and the other bouncing is normal. If I take a closer look here, I think I still have some bouncing at the beginning, but this is normal before the contact converges. Now I want to drive the wheel, and also add a couple of sensors to the body of the inverted pendulum. So I'm gonna use it later for control. But first, driving the wheel, as I showed before, here on the joint you can use the driver tab to drive any joint, and it gives you a lot of options. But these options, for example, driving it directly with a polynomial function, these options are going to be specific to that joint. However, a better solution is to use this driver option. So by defining a driver, it's going to be available to be applied to any joint. For example, now I select this joint, I have the same options, and later on I can add this driver to another joint. So here I drive it with some velocities. Let's put it on RPM. Let's say 100 RPM. And just to see what is the direction and if everything is okay, I'm gonna scale this up. This is just a display scale. So that's the way it shows on the screen. So this brown pin thing is the joint, and this shows the direction. Since this is not the forward, I want to uh, turn this back to the other direction. So positive velocity is along the direction of the slope. And the direction of driver is going to follow the vector of the joint. The vector is this way now. I just need to reverse direction of the vector and click OK. Now you can see the positive driving speed or displacement is as I like. Of course, there is no difference. I could just use negative velocity here. Under the velocity, I could use a negative 100 RPM, and it would do what I like. But it's better this way. It keeps everything more simple. And I can bring down the scale a little bit. So now it's going to turn with 100 rounds per minute. Let's run the simulation and see the result. So as you can see, it's turning. The friction is not bad. The body is too heavy compared to the wheel. This is 300 kilogram. One option, of course, is to make this lighter with material or remove some material so it behaves better. But this is as we expect. So it moves, the wheel moves forward, and since on the motor joint we define action and base, it's not action only. We could define a joint without a base, but it is action with base. The motor or the drive is also going to follow that and hold to the base while turning the wheel. So that's why it makes the body fall faster. So as the wheel turns forward, it pushes the body backward as well. But we could apply a velocity or torque only to the wheel without holding to the body. That may not be possible in practice, but in theory it is possible, and you can define it here. Now to control this later, I need a couple of information. I need to read a couple of information from the body of the robot. To do that, we need to add sensors. Sensors are returning displacement, velocities, acceleration, and forces. And you can read all directions and orientations for each option, and you can read absolute, relative, or relative to something that is user defined. But to define a sensor or to attach a sensor, you need a point. So before defining a sensor, you need to define marker. Markers are basically points on objects. So here I select this motion body as object, which is the body of the pendulum. And then I need to specify a point. Make it simple. I'm gonna pick a point on the top. Here, gonna go with between 2 points. So between these 2 points, so it's on the center. And also make sure that the coordinate system is as you want, because the sensor, the data that the sensor is returning is going to follow this coordinate system. I click OK, or maybe I'm gonna make the scale a little bit bigger so it's more visible and easier to see everything. So this is my coordinate system for the sensor. Now I can define a sensor. Note that here I also have a smart point. Smart point is exactly like a marker, but you can put it anywhere you want. So a smart point doesn't need to be on an object. You can put it anywhere on a space. So I go back to sensors, and here I select the marker I just made. Now I can extract any information from this marker, which is attached to this body. I need a couple of information. I'm trying to define an IMU, so I need acceleration along all directions. For the X, I'm gonna call it X acceleration, and then Y. And since I don't have a frame of reference, I'm just going to use absolute. But you could have it relative to the ground, for example. If the ground or something else is moving, that would be more useful. And the Z acceleration. And also I want to have the rotation along the x-axis, which is the rotation of the body along this axis. I'm again going with the absolute. So here I need to select the sensor, rotation along x-axis, absolute, and this is going to be x rotation. And okay, so I have the sensors, and then I need to also read the torque on the joint. Now I define a new sensor, I select the motor, it gives me this option of selecting force. It says force, but you can of course select torques. So I'm going to select torque along x-axis, which is the direction of rotation. Let's go ahead and motor torque. Now I have all this data to output to MATLAB, and I want to input the rotational velocity of the motor. So I need to define some inputs and outputs to connect it to MATLAB. To do that, here from the menu, I can go to Insert, Plant, define a plant input, which is going to be motor velocity or voltage or whatever we are going to send from Simulink to NX. And also I need to output all this information from the sensors to the Simulink. Go with the output, brings all these that I want. For each one, I need to define a new output name. This object exists, so I'm going to just double underline it. And we have all the inputs and outputs. but we are getting the input from Simulink, but this is not connected anywhere. To connect this motor input or plant input to the motor joint, I need to first define a function. So I go to the function manager. Here I click new function, write the name for the function, and here in the formula we can't write anything in the function. And if you click apply, it will make a function. Here you get an error that the dimensions don't match. NX is using this thing that checking the dimension on both sides of a conditional if operation. It doesn't make any sense, so you have to change that first. If you go to the file, preferences, and motion, here it has mass function unit policy. You have to put it on ignore units. So when it compares the stuff, compares numbers, it compares 1 to 1, not 1 millimeter to 1 meter or something else. It will return only numbers. And now I can go to the driver and use this function to drive it. So I'm connecting this input with a function to this driver, which is driving the joint. I select function. Here from the function manager, I make a new function. And in the formula, I can use this plant input and the input that I already made, the motor velocity. You can check the syntax by clicking on this check mark. Click OK. I have the signal 1. And now signal 1 is going to be the velocity that is driving the drive 1, which is driving the joint. So click OK. And now the motor velocity input, which is being dictated by Simulink, is going to be the velocity of the joint. Before you start a code simulation, you need to set up the path of the Simulink you have inside NX. To do that, you move to Files, Utilities, and under Customer Default, here you move on to Simulation, Motion, and under Analysis, you go to Recordine tab, and then set the path to the MATLAB under Windows. So here, let me show that you have actually two MATLAB files. That's three MATLAB files actually. One of them is here on the bin. This file is not going to work because it is going to run one of the main MATLAB files under 64 or 32-bit. So what you need to do, if you have, if your Windows is 64 bits, you move to the 64 folder here as the Simulink executable. Then click OK, and now you need to restart your NX for it to take effect. Now, because I have planned inputs and outputs in the simulation, if I click on the solve, it's not going to solve the simulation, but it will ask for a co-simulation setup, which there are two. You can use these NX as a host program. This way, it will run MATLAB from NX, and I will wait for MATLAB to send commands. Or you can use Simulink as the host program, which is easier and most stable one. So here I'm going to use Simulink as a host program. If you click on apply and go back to the same folder that you are doing the modeling, you will now see two files that are just made. If I sort them by modified date, these two files are just made now by NX. The first file is setting the conditions. If I open this one, it is setting some conditions like how many sensors or how many inputs and outputs I have, what are the names of them, what is the time step is being dictated by Simulink, and other options that are needed to set the communication between Simulink and NX. The second file is actually what we need, and it is first running the first file to set the conditions, then it runs the NX client. So to set parameters, as you can see here, to initialize the plan, I need to remove this comment and then run this from MATLAB. Here it starts the MATLAB Simulink and NX communication and waits for information from NX. Now it gives you this NX motion plan block, and make sure that it says client here. If you run NX as a host, this block is going to have host region here. So everything is okay. Also, I can double click here and see details, which is as I expect. I only have a motor velocity and I receive a couple of accelerations and other stuff from the sensors. So I go back, and now you can use this to control the pendulum that we have here. Don't need that window anymore, and everything is going to be controlled from here. So next, you don't need to actually touch this control system that is made in Simulink or the Simulink file. You have to make a new blank model in Simulink. I only use this file, and you can close this because it's just a template that we are using and we don't need it anymore. So now I have this control block here, which is connected to NX, of course. To test, I'm just going to add a constant and try running the motor. So I'm going to send a, let's say, 500 command to the motor, and I'm going to read all the information. I have 5 outputs, so going to connect all the outputs to the sensor, and later we can check this scope to information we have in MATLAB. The time is going to be set from here. I'm going to have it for 5 seconds. I remember that the model from Simulink is going to read files in the folder, the PRT files and simulation files in the folder. It has no direct communication to NX. So remember, you have to save every time you make a change. If you don't save, it's going to read the folder and your files are unchanged, and it's going to read the old files. So every change you make on NX, save here and then go back and run your model. So now the Simulink model is running, and it will show you some messages if the simulation is successful. You also, on the result on the left side, you're going to have a result file after it's finished. So on the status, I can see that it's running. Simulation is solved successfully. It just started to run the time steps. And now the simulation is done. I can now go back to the result and run it. So now you can see this looks like actually 500. It's a lot faster. And if I go back here to my scope, I can see all the information that is being sent from the NX. So next step is to make a control loop to balance the segue or inverted pendulum.